Hi, this is the beginning of the chapter 4.3 notes, and it's on Riemann sums. And first of all, the Riemann sum simply says that if you, oops, guess what? Don't have a brush to write with. All right, let's try this again. If you have like this, you can approximate the area of this with rectangles. So I can break these up into rectangles. More specifically, these rectangles do not need to be of equal width to get an approximation. And so I could have something like this, and it calls each of these widths, these unequal widths, a partition. So what I do is I've taken the function and I've partitioned it into, in this example, 4 rectangles of varying widths. Well, the more rectangles of various widths that I put in that, underneath that curve, I could fit those rectangles and get a better approximation. The symbol of a partition is this. That's the symbol of a partition. And the rectangles that we've been doing before have been of equal length, but they don't have to be. And as you partition that function into more and more rectangles, those partitions, the lengths of those partitions, are heading to 0. So Riemann sums defines the area in the curve slightly different than what we do. First of all, this partitioning heading to 0 is like delta x heading towards 0. So these rectangle widths are getting smaller and smaller and smaller, but they could be of unequal length. And for each rectangle, you'll have a height, and that height is somewhere within that rectangle. Maybe it's a left endpoint, maybe it's a right endpoint, maybe it's a middle endpoint, but it's somewhere between there. And then you have this delta x sub I, and the reason it's sub I here is because it's between differing partitions, so it's not necessarily of equal length, but it's heading towards 0. And so it's very similar to what we've done. In fact, when I do example 1, I'm going to do it in the same fashion as I've done before, but this Riemann sum can be written in this fashion, in what we call an integral. And this is called a definite integral. And it looks like an indefinite integral, but it has basically 2 bits of differences. It has an a and a b. It's telling you between what 2 values we are computing the area. So there's our a and our b. And we're going to use this process for this unit to be able to figure out the area under the curve. So this is saying, all right, we're figuring out the area underneath the curve. This is the function. This is my height. This is my width of my rectangle, and I'm figuring out the area between these 2 values. All right, and again, here is my indefinite integral, and sometimes I say it has a hat and a boot because my snowstorm idea. This right here is a goofball thing. I don't know where that even came from, so don't even ignore that. But again, here's my height, here's my width. That gives me my area. And more specifically, this area is what we call net area. It's not total area, because we could have some area that falls below the x-axis. And whatever falls below the x-axis, this area right here, is considered negative. And this would be considered positive. And by the drawing that I made here, the positive part is a little bit more than the negative, but that negative would take that positive down. So I would get a resulting net area. Is it sometimes possible to get a negative area? Yes, it is. And we're going to talk more about that later. Alright, so let's take a look. Here's my indefinite integral, and I know that because I got an a and I got a b. So b minus a divided by n is my delta x. And my c sub I is going to be 0, that's my a, plus 2n times I. So basically 2I over n. And I'm going to take the limit. Notice that process hasn't changed. As n goes to infinity of an infinite number of rectangles, and I'm adding the areas of those. And I'm going to have 2 times 2I over n. That's my function times my width, which is 2 over n. So I get the limit as n goes to infinity of the summation of I equals 1 to n. Now if I compute this, I'm going to have 2 times 2, which is 4, 4i over n. Now multiply it by 2 over n, so I'm going to get 8i over n squared. And then I'm going to rewrite that as the limit as n approaches infinity. I'm going to take out my constants, my 8 over n squared, and I've got my summation of I equals 1 to n of I. And now I'm going to write that in my explicit form, and I'm going to have the limit as n goes to infinity of 8 over n squared times n plus 1 over 2, and that's going to give me the limit as n approaches infinity of 4 times n plus 1 over n. And I can think you can see the leading coefficient here, and both of them are going to have a degree of 1, so my leading coefficients are 4 over 1, which means I have an area of 4. Now another way to look at this is I could have used geometry. My y-intercept of this equation, 2x, is 0. And I'm integrating it from 0 to 2. So right here, here's 1. Right here, here's 2. And if I plug in there, I get a point right here, 2 comma 4. And I can make this triangle. And the area of a triangle is 1/2 base, which in this case is 2, times the height, which is 4. And if I multiply that, I get 4. So the area of this geometrically is 4. Using calculus, it's also 4.